In this example, we have a bus traveling at positive 9 meters per second when the driver comes to a sudden stop to avoid hitting a dog. The braking period lasts 1.5 seconds. Find the acceleration of the bus. And you're assuming it is uniform acceleration. All right, so like every problem here, let's visualize what's going on. Part of the reading comprehension is to be able to put a picture in your head of what's happening. So I'm going to show that by drawing a quick little sketch. There's my bus. It's moving along. I'm going to draw an arrow to represent its velocity, and I'm going to label it as 9 meters per second. All right, it's on the road, and it's going to have some animal up here. Forgive me for my poor effort here at a dog. All right, there's some ears, and there's its mouth. There's our dog. So this thing's moving along for a period of time, 1.5 seconds, and it appears it hits the brakes. All right, so let's identify some of the things. Let's say we have an initial position, and later this bus is going to start hopefully short of the dog, right, at some final position. We have a velocity of 9 meters per second. We can label that v. We have a time, and if it's changing its velocity, then we have an acceleration a. And this is where it's important to understand what direction acceleration acts. So one thing you might have noticed was this positive with the 9 meters per second. That has indicated that the problem has dictated that whichever way the bus is currently moving, we are calling that the positive direction, which means if we are going to be slowing down, if you think of acceleration like a push on an object, well, that acceleration would have to be pushing to the left. So hopefully that's a cue that your acceleration is going to be negative. All right, so we've identified these things. I like to organize them in our ATVX table, right, which is really just the variables that come into play with that, our equations. We have acceleration, time, velocity, and because it's changing, initial and final come into play, and position, which we can start somewhere and we potentially finish somewhere. All right, so by identifying what we have in a table, it makes it a lot easier to figure out what we have and what we want to find. All right, so in this case, it says find the acceleration. So I'm going to put a little star next to that a value because that's what I'm trying to find. And I also know, based on my picture, that a better be left. So I'm going to make sure I understand that it is going to be a negative value. If right is positive, then a must be negative. We know the time, 1.5 seconds. We know the initial velocity of positive 9 meters per second. The final velocity is not given as a number, but it comes to a sudden stop. All right, so these are some key things you're going to see in these problems. There's context clues to help you fill in this table. So this bus must stop, all right? And so we're going to put it at 0 meters per second at the end. We haven't dictated where it's located, but we can always define where we start to be 0. And then where we finish is going to be an unknown. All right, so really I have two unknowns in this problem. We want acceleration. If I look ahead, I've got my two equations up top. I've got equation 1, which is my position function. It's where the bus is going to be located at any given time, given some initial velocity and some starting position. And equation 2 is the velocity of the bus at any given time, given an acceleration and some starting velocity. And so every single problem is going to have these two equations, and we're going to use them as needed to identify what we want. We obviously want A, and so we want to pick an equation that has everything except A. So I like to put a dot over the things I have. I have time, I have V initial, time, right? V initial, all right? And a question mark over the things I don't, right? And if you notice, the first equation I have two question marks, so I can't solve for either one. However, this second equation, right, I have A as the only unknown, so I'm going to use the second equation, and I'm going to plug in what I know. V final is 0 meters per second. Acceleration is what we don't know. The time is 1.5 seconds, and the initial velocity is positive 9 meters per second. And now I'm just going to take that equation and I'm going to solve for the acceleration a. And when I have that, I should have my answer. All right, so now it's just an algebra problem. Let's isolate my a term by subtracting 9 meters per second from both sides. Now, just for the sake of keeping things so they make sense, I am writing the units in there, and I think it's helpful, especially when you're starting your problems, to write them in because it helps you see how they tend to work out if you use the right units. 1.5 seconds. And now if I'm solving for a, I'm going to divide everything by 1.5 seconds on both sides. And here again, we look at our units. So now a is all by itself. And on the left side, we have a negative value of 9. Let's go in here. I can clear that. I have 9 divided by 1.5, and I get 6. So A is -6, and look at the units. Meters per second is meters per second squared. So there was my answer for this problem. This truck will lose 6 meters per second of velocity every second, which makes sense. After the first second, it's lost 6. It's now going 3. And after another half second, it'll lose another 3 meters per second. So in 1.5 seconds, it will subtract away 6 meters per second every second, and therefore it'll reach 0 at 1.5 seconds. So hopefully that kind of makes sense and is a number that we would expect as an answer.